Welcome back everyone to section number 3. This is just a nice one-page long video here, the last one for this section. This is points of inflection. So we're going to go ahead and define these things called inflection points here. And then we're going to practice, finding these things given a function's equation. And more or less the story goes that when a function switches from increasing decreasing, that is when its derivative changes signs, right, something interesting happens. We get local minimums and local maximums, and those are nice to visualize on the graph. The claim is when you change concavity, right, when your second derivative switches from positive to negative or negative to positive, something nice also happens. And these things are called inflection points. So that is going to be an inflection point there. So it's a point on the curve, y equals f of x. This is the inflection point. If f is, first of all, it needs to be continuous there. And then either the curve changes from concave upward to concave downward. That is that the second derivative is greater than 0, and then the second derivative is less than 0. Or if it changes from concave downward to concave upward. So that is the second derivative was less than 0, but then it becomes greater than 0. So like I said, we're going to get an interesting point on the graph when this happens. So let me go ahead and maybe sketch one out here. So I'm going to have a sort of situation where the function is maybe first concave down. So if you were to draw out its tangent lines, right, it would lie below its tangent lines. So it's concave down, and then I'm going to switch to concave up. So concave down to concave up, something like this. Now if you were to graph tangent lines here, you would see that it's above its tangent lines. So this point right here, maybe in blue, this is our inflection point, which I often denote INF point. This is not infinity, it's inflection point. Now let me go ahead and continue the graph. If I was continued to be concave upward here, and then all of a sudden I switched, right? So again, this is all concave up, it's above the tangent line, and then I switched and I became concave down, going off the page a little bit there. But now you can see that the function lies below its tangent lines, so this is another inflection point, and this is kind of going the other way. Now notice something interesting about the derivative at these points. At this one right here, kind of the derivative is the most negative. It's the steepest downward here. So it's kind of the derivative was negative, it became more and more negative, and then this is the steepest point. And then after that, it kind of starts shallowing out. Likewise, over here, this is where the derivative is the most positive. So the derivative is more and more positive, and then here it's its most positive, and then after that it starts kind of shallowing out. So inflection points, they're kind of where the slope is the most extreme, either the most positive or the most negative. All right, so you can see we're interested in where does the concavity change. Well, just like for the first derivative, where we were really interested in where was the first derivative equal to 0 or undefined, because this is where the increasing decreasing could change. Now we're interested in where the second derivative is equal to 0 or undefined, because that's going to help us figure out maybe when the second derivative changes or when our concavity changes. All right, so let's get a little bit of practice actually applying this to some problems that you could see on quizzes, exams, homework, stuff like that. So here's a nice one because it's already giving us the second derivative. So suppose f is a nice continuous function, and here is the second derivative. So we don't even have to do any work for this one. Find where the function is concave up and where the function is concave down. Where are the inflection points? Okay, so this is going to be the same sort of strategy that I applied for the first derivative back when I was thinking about increasing and decreasing, but now I'm going to apply it for the second derivative. So okay, maybe the first thing I ask myself is where is the second derivative undefined, right? Where can I divide by 0? Where can I take the square root of a negative, things like this? And looking at it, the answer is nowhere, right? This is a relatively nice thing, so unfortunately, we're not going to get the second derivative being undefined anywhere. Now, okay, where is the second derivative equal to 0? Okay, well I can solve that. Set 0 here, and I have x plus 1 quantity squared times x plus 5. And in this case, well, there's no work to do. It's already factored. And so the only way that this can be equal to 0 is if x is equal to negative 5, or if x is equal to negative 1. right? Because that would make each of those components equal to 0. Okay, so just as before when I did this for increasing, decreasing, I'm going to draw out a number line. I'm going to have -5 and -1. And now I'm going to be plotting stuff about the second derivative, right? No longer the first derivative, but about the second derivative, because I'm interested in concavity, right? Because if this is positive, then it means concave upward. If the second derivative is negative, then it means concave downward, right? So I'm interested in the second derivative. But the strategy will be very similar. So I'm going to go ahead and choose test points, maybe something like -6, maybe something like -2 and 0, right? So these are test points in each one of those intervals. And now I'm going to go ahead and plug those back into my second derivative to try to figure out if the second derivative is positive or negative there. So, okay, maybe I'll go ahead and plug in -6. So that'll give me -6 plus 1 squared, and then -6 plus 5, so that's going to be -1. Okay, so -6 plus 1, that'll be -5, but when I square that, I'm going to get 25 times -1, so that's certainly less than 0. Okay, so we have negative over here. How about if I plug in -2? So -2 plus 1, so that'll be -1 squared, and then -2 plus 5, that's going to be 3. So I'm going to have 1 times 3, that'll be 3, that's going to be greater than 0. So when I plugged in -2, I got a positive number. And then finally, if I plug in something like 0, so 0 plus 1 squared, so that's going to be 1 squared, and then times 5. So that's going to be 5, which is certainly greater than 0. So positive. Right? These things don't always alternate, so this is true here. Okay, so again, our question was, where is the function concave upward, where is the function concave downward, and where are their inflection points? So I'm going to say f is con up, so concave up on -5 to -1, and then again from -1 to infinity, right? But not including that -1. F is concave down on -infinity all the way to -5. F has inflection points at x equals, and remember, inflection points are where we switch either from concave up to concave down or from concave down to concave up. So we have one at -5, but then we don't have one at -1, right? Because this is from positive to positive, so we don't have a sign change, right? It needs to go from either positive to negative or negative to positive. In this case, it stayed positive to positive. It was concave upward, then it was still concave upward, so there's no inflection point at -1. All right, and there is our final answer. Let's go ahead and try one more. I recommend pausing the video for 2 minutes, try to get as far as you can, and then I'll spoil the surprise. All right, so this is how far I've made it. I calculated out the first and the second derivative. I got 6x minus 2. Remember, concavity is asking something about the second derivative. Is the second derivative positive or negative? So in order to figure out where this was positive and where it was negative, right, I tried to figure out when it was undefined or when it was equal to 0. Well, it's never undefined. There's no division, there's no square roots, anything like this. So it's equal to 0 when x is equal to 1/3. So hopefully you got to the same point as me. I went ahead and I plotted the point 1/3 on a number line. And remember, I'm interested in the second derivative. Where is the second derivative positive or negative? That's what tells us something about concavity. So now I'm plugging in our test points into the second derivative. So I chose the test points 0 and 1. You can choose really anything, so long as it's right. This test point should be less than 1/3. This test point should be greater than 1/3. So if I choose 0 and I plug it into the second derivative, this is going to give me 0 minus 2, so that's going to be, well, -2, which is certainly less than 0. So therefore over here we have negative. Likewise, if you choose 1, you're going to have, let's see, 6 times 1 will be 6 minus 2, that'll be 4. That's greater than 0, and so over here we have positive. All right, so therefore, Well, where is it concave up? Where is it concave down? I'm ready to answer those questions. F is concave up on 1/3 to infinity. F is concave down on negative infinity all the way up to 1/3. F has an inflection point at x equals, and notice there is a change of concavity here, 1/3. So x equals 1/3. And that right there is my final answer. And again, we want to recognize kind of what we have done here. I know this just seems like a lot of manipulation of variables and numbers and stuff like this, but let me go ahead and show you really quick on our Desmos what we've done. Right? So here's our nice function, our x cubed minus x squared minus 5x plus 3. I went and I graphed the tangent line here, so you can see over here it seems to, the tangent line is above the function, right? So the function lies below its tangents. That means it's concave down over here. Concave down, concave down, concave down. And then all of a sudden right in here somewhere, right, you can see that the slope seems to kind of be at its most negative. Right, so it's kind of getting more and more negative, and then after this point it starts to kind of shallow out. Right, so after this point you can see that we've made a change, that actually now the function is above its tangent line. So again, the function was below its tangent line back here, and now there's all of a sudden some change. It looks like it's right on top of it here, and then past that, well, it seems to be above its tangent line, right? So it switched from concave down to concave up, right, above its tangent line. So somewhere right around in here it switched, right? And so the claim is, well, exactly at 1/3, right, it made this switch. It was concave down and then it switched to concave up at 1/3. And so again, this kind of shows us this is like the most negative slope right here. And after that it starts becoming more and more positive. The slope's increasing. All right, so that's what we were able to do. Again, you kind of sometimes lose it with all of these variables and numbers and stuff, what you've actually accomplished. So it's nice to every once in a while go back and graph these things and see what we've done. All right, that's it for me and for this video. I'll see you guys later.